around a certain point. It's an infinite discontinuity. The gap between this part and this part is infinite. And these are the three types of discontinuity. And in some sense, they're more and more severe. The first type of discontinuity, if you're dealing with almost any property of a function, you can essentially ignore it. That's almost, removable is almost simultaneous with ignorable. Unless you're actually considering the exact behavior at that point, you can ignore that discontinuity. You can do something called integrating over it. You can do differentiating everywhere else. The second type of discontinuity, if you're doing a process called integration, you can ignore the second type of discontinuity. You can ignore that one. This third type of discontinuity, even when you're doing something called integrating, you can't ignore it, and it might actually screw up your function. It might not, it might. This one will screw up your function. Some of them don't necessarily. Like, I haven't discussed integration yet, that's a while ahead. But if you'd have 1 over x to the 1/8 power, you could integrate that from 0 to infinity without getting a problem. Or no, you couldn't integrate it from 0 to infinity. You could integrate it from 0 to some positive real number a without getting a problem. But you couldn't integrate 1 over x from 0 to some positive real number. That doesn't work. But anyway, that's a property called divergence and convergence, and that's a little more complicated. But I believe I've discussed enough about limits and the mathematical definition of continuity that next time I can actually get into talking about what a derivative is and how you calculate a derivative. It's a fundamental part of calculus, and it's absolutely essential to physics. So next time I will discuss, I'll introduce, we'll start on differential calculus. We'll start on the sorts of things that you encounter in differential calculus.